Hey, good afternoon, everybody. So good to see you. I know the time is late. Most of us during this time kind of either wrapping our task at the end of the day, jumping into the shuttle, or walking home, or taking the bus, or driving home. So I really appreciate you taking the time to join me today and the rest of the community to learn and explore and see what more things you can do with Iceberg and Kafka. Anyone here has Kafka in production? Kafka running in production? See a little bit of hands? Iceberg in production. Okay, that's exciting. All right, no more fragile pipelines. So the story today, I'm going to tell you how a company named Confluent, I don't know if you heard about Confluent. Confluent is the original creator of Apache Kafka. So how a company named Confluent built a solution for our customers to bridge in between Kafka to Iceberg. What are some of the learnings we gathered throughout the day, and how we build our architecture behind the scenes to support thousands of customers that running it on a daily basis. So what did we do, and how did we make it declarative? Welcome, new people. Hello there. So what did we do, and how did we make it declarative? Essentially in Confluent, what we have, if you've never seen a Confluent environment, you can have Kafka topics and you can manage them directly from the UI. And so the only thing we added is kind of like this product named Tableflow, and a click of a button saying enable Tableflow. And once you click it, it opens another UI for you, and it asks you which type of table format do you want to work with. Is that going to be in Iceberg? Is that going to be in Delta? And then a couple of more questions around latency and so on related to data streaming. And of course, data catalog that you want to work with. So you're deciding where you want the data to land, which data catalog to integrate with, and so on. While building that product, we learned a lot of things. One of the things is intuition is not your friend. We're thinking about Kafka, thinking about Iceberg. One of the key areas that people went to, and one of the reasons we actually built that service, is people immediately went to connectors. Hey, let me just take an Iceberg connector, let me just take a Kafka connector, or let me spin a Spark job and just dump everything in, or a Flink job, and so on. But what we realized is, really, we identified become well stupid in that space, because there's a lot of challenges related to actual intrinsics of data that we couldn't just avoid. So how would a simple connector would look like? Essentially, what you're seeing here, this is a streaming insert where you have a table of Kafka as a source, you have an Iceberg as a sink, and you have some job running, bumping the data into an Iceberg sink from a Kafka source. This does not work and couldn't be operationalized at the scale of a company. It will only work if you're doing kind of like a dummy project, some capstone, and so on. And here are the 3 reasons why it didn't work. 1, schema evolution. In real life, our schema changes. We have a lot of complexities around schema, especially if we have different Kafka topics where we have different producers producing their schema. There's not always alignment. It takes time to create an alignment. So that was one of the challenges. Second one is consistency and partition. The data is saved in a specific partition in Kafka. How does that reflect in my Iceberg storage? It's not exactly a one-to-one. And the third one, small file and compaction. Similar, but thematically, if we want to just take all the data that we have event by event and dump it into storage, we will end up with a lot of small files, something that is unacceptable in the analytics space. So we faced a list of questions, a lot of questions related to 2 different categories. One is materialization. What does it mean for my schema to change? How do I monitor all these changes? What do I do if things breaks? What should I do about that data, right? I need to make a decision. And how often do I create a new Parquet file? Because I want to optimize for cost versus latency. On the maintenance side, how do I do that optimization? What's the best trade-offs? And how to actually schedule and run it. As you can imagine, a lot of bugs, a lot of exceptions, and so on. I'll say a couple of things about me. If you don't know me, I am a deep Polak. I wrote 2 books for O'Reilly, one on scaling machine learning, and the second one is High Performance Spark, the 2nd edition. People manager, I have more than 15 years experience in the industry. I started my career in ML, and then I moved to big data, and today I'm with Street. So let's get to the basics to understand a little bit how these 2 things work. Let's talk about Kafka. Many of you said that you have Kafka and you're working with Kafka. So what do we have in there? We have a Kafka producer that serializes the data. Excuse me. The data is getting into a broker, some topics, and then a Kafka consumer that deserialize the data. One of the challenges with Kafka topics that it can support multiple versions in it. It's kind of like a magic. Put whatever you want in it, it will just take it and process it. This is where schema evolutions start to be a problem, because we want to support different formats, different edge cases. We want to support semantics of tables that usually Kafka doesn't support out of the box, like append and absert. We want to be dealing with bad data. We want to automatically infer schema if we can. And then to convert and maintain the divide, right? We want to make sure we have a healthy contract between these two Kafka to Iceberg operations. When I'm looking at Kafka, Kafka has a key value mechanism, essentially a record of bytes that exist there with different formats, Avro, JSON, protobuf, just bytes, versus Iceberg that has a more constructed schema like secret data types, table with columns, row stored in Parquet, and so on. So you can automatically see how my key value can be anything in Kafka versus in Iceberg that have specific schema. So what I want to do, I want to deserialize the byte, infer some schema, understand what happens in that schema, right? Apply the schema evolution that I need to, and then update my Iceberg schema back in. But I'm facing the challenge that I can have different schemas with different values. It's not always consistent. So what do I do? How do I go about changes of schema versions that are not always compatible? One option is to rely on an external tool named Schema Registry. Schema Registry enables me to manage the schema outside of Kafka, and it works together with Kafka throughout deserialization and deserialization process. It has 3 different compatibility modes, something to think about. One is backwards, so consumers can read previous produced data. One is forward, where you can consume old schema and read newly produced data. And one is full, so it works both sides. Of course, it works with the serialization, deserialization implementation. And Schema Registry can also allow me implement pattern named DLQ, that letter Q, essentially for every bad data that doesn't conform to my schema, doesn't conform to specific rules that I can build in it, I can dump it into a DLQ so it won't go downstream to my Iceberg. So this is one thing that we can do with Kafka specifically. On the other side, we have schema management in Iceberg that is completely different. So it allows me to add, to drop, rename, update, reorder, things that Kafka doesn't necessarily enable me as kind of like infinite immutable log. Iceberg has automatic schema evolution. So essentially, we can give default values to columns and start adding more columns to my schema. It supports deletes, right? I can mark stuff in deletes and then take care of them later. And it supports a different type promotion than what Avro and what Iceberg, specifically with Parquet under the hood, enables to promote. So the promotion, Avro is a more permissive type promotion. If you ever look at things like int, it's easy to promote it to long, float to double, and so on. And in Parquet specifically, type permission, the type promotion permission is a little bit more restrictive than one available for me in Avro. In Avro, the goal is don't lose data, essentially. So how do you do that transformation between the 2 schemas, and what are the different options that we looked at when we developed that solution? 4 different ways. One is stop the world. As an engineers, we don't like to stop the world. We want to continue having things running in production. Stopping the world is costly. We cannot really afford to have production down for a week. So stop the world is an option, only in very specific edge cases. Ignore bad changes. This is something that we can do, but sometimes that means that we're going to dump data that we might need to take care of later on. So how do we make sure we are still keeping that data so the flow can continue to happen to exist? Third one that I talked about with Schema Registry, this is the DLQ. So we can write any bad data that I have or any data that doesn't confirm directly with my schema into a dead letter queue and just continue from there. And the fourth way to go, and this is what we implemented Confluent, is adapt the schema to handle the change, which means we're going to create what we call an Uber scheme. that is going to be a combination of all the different permutations of that scheme. So each customer can decide down the road which type of format, which type of roles they want to take. So all the data from Kafka is automatically streamed into Iceberg into an Uber schema that contains all the data that was beforehand in Kafka. And then the customer, on the customer side, they can decide what to filter, how to go about it, and so on. So this is the solution that we decided to go in order to avoid all these troubles down the road. Each one of them has pros and cons. The table schema not always corresponding to the Kafka topic schema that we had there, which is okay because we expect the Iceberg schema to be slightly different, given that in every Kafka topics there could be many different versions of the table. The pros is no information is being lost, which is something that we want, and fewer chances of incompatible schema changes and breaking consumers. So this is how we solve the world of schema evolution. Second challenge is consistency. So if I have my Kafka cluster, Kafka essentially stores all the data locally on disk, and we can also spill to any service that exists in the cloud if we want to spill some of the data for people that are not aware. And so we build that service named Tableflow that essentially acts external to my Kafka cluster, and the goal for Tableflow is to coordinate that Kafka to Iceberg operations. So what happens there? Kafka cluster specifically, if you're not familiar with that, there are partitions, and each partition is saved as a segment. So we're going all the way low level to manage the segment. In Confluent specifically, we went all the way low level to manage the rack where the data is saved, so we can optimize to the millisecond that we want to be optimizing it. We're fetching pointer to the segment, kind of like you can think about it as a URI, a location to read, and then we're sending it to Tableflow. So more data is being transferred through Kafka cluster. That removes the bottleneck of transferring everything through the broker. If I am transferring all the data through the broker, it's going to create a huge bottleneck, something that we both know. If you're still your Kafka cluster struggling because of different connectors, it's because you have consumers that's kind of killing that Kafka cluster, and you want to think about what is exactly that you're doing from a consumer side. So we didn't want to kill Kafka cluster. We want to have it continue to operate in the scale that we want. And so we're fetching a URI to that segment, and we're passing it to the service. Second step is the service wants to fetch that information from my object storage. So it will speak directly to object storage with all the permission and security around that, and will bring the information that it needs, including number of partitions. It will calculate how to polarize the consumer, how to read, how to materialize, and so on. So this is kind of wrapping around consistency for Kafka. We know exactly which data we brought in. So we need to know the partition, we need to know the offset, we need to know the segment, and we need to have better parallelization for all this process so things doesn't go through my Kafka broker. We want to offload this from Kafka. So this is a learning for all of us that kind of building similar solutions. Now, consistency is Iceberg is slightly a different conversation. Iceberg has what we call optimistic concurrency control. So essentially it blocks some of the read and some time, depending how we are optimizing the consistency aspect of Iceberg. I'm not going to go deep into it. It's really interesting. There's a great blog post in the bottom. Highly recommend reading it. That goes into the intrinsic of everything related to Iceberg consistency, how to configure it, copy and write, copy and read, and so on in all the great snapshots, etc. But what I can say is if I'll break down a little bit more deeper into the Tableflow service that we build, essentially we have two microservices, two high-level microservices. One is the materializer, and the second is the committer. As we want to make sure we have consistency in between these two distributed frameworks. So my materializer brings the segment URI, and then it communicates with the cloud storage to bring the data and also upload the data. And then it gives some commit to the committer. The committer will go back all the way to my object storage as well, where my Iceberg table lives, where my catalog lives, and you commit the metadata that Iceberg requires me to commit for my catalog. And then it validate that actually everything was written at the end. Once everything was written at the end, it will commit the offset back to the materializer. And this is essentially how we're closing the loop in between that by having kind of like a two-phase commit, if you think about it, algorithm across the different microservices that works together. So this is how we solve that aspect of consistency. Let's talk about small files and compaction. Like I mentioned, like a lot of people mentioned, they talked here about streaming in Iceberg. Once we have streaming and ingesting a lot of data, it means we're creating a lot of small files, which is a big no-no for analytics world. What happens there, it creates metadata overhead, high IOPS, slow query performance. This is an example of Unity catalog, how the data is being written to actual storage in the catalog. And you can see the low level, essentially what we have there is all files. So we want to make sure we don't have a lot of files in it, so it's easier to index and reach the data as we need. But get file by itself, if we need to reach the version, the schema, and so on, everything like that is an I/O call. So we want to eliminate that. There's a great presentation that I'll share at the end if anyone is interested of why small files is a problem, really diving into the IOPS and the structure of Parquet. But again, it's a whole conversation. So what are some of the compaction strategies that exist out there? A lot of people here talked about compactions throughout the day, and I want to share some thoughts and ideas. There's a lot of compaction strategies to go about taking all the data and making sure it's ready for analytics. Bin packing heuristics combine all the file efficiency and respect constraints like file size, partition boundaries, sort order, and other things. Trigger condition is kind of helping us by the number of size, kind of give us a more generic approach. Size aware policy, let me know if you reach that specific size of the bucket so I can start compacting right now. Metadata, it's more on the Iceberg side of how things work, or partition aware compaction. We want to make sure we want to avoid shuffling that is really heavy compute on the analytics side and ensure some query pruning. So we need to have more information about what is the data and what is the queries and indexes in order to do more partition-aware compaction. So what did we do in Confluent and what did we implement? Because we're serving thousands and thousands of customers who don't have the privilege of diving deep into what exactly the data and how is it being queried later. Again, we're a data streaming company, analytics companies. There's a lot of great companies that knows how to do that, but we're focusing on the data streaming side. So for us, we decided to go with trigger condition, which means once we reach a specific number of files, specific thresholds, or specific time, we will run that compaction. This is how we're kind of like making sure we're not dealing with the logic of the data itself. We're kind of like disconnecting ourselves from that, and we're looking at metrics that are very hierarchy-like, very straightforward, and file-level metrics that we don't need to deal with what we call some smart merge decisions. There's a lot of way to do smart merge decisions, and a lot of data warehouses implements that. But again, requires more knowledge of how you're going to query that data, accumulating statistics of how people are querying the data, and so on, that we don't do. Overall, necessary optimizations that we do for our customers with Iceberg. Through that snapshot, we make sure for every interval we're doing that. Garbage collect and reference file, critical. Compact metadata files will also be that, and compact the data files itself. So these is kind of like all the learnings that we had to implement for small files. So a little bit of recap. We have a couple of last minutes. Kafka to Iceberg connectors doesn't work for scale, doesn't work out of the box, doesn't work when you need to support thousands or hundreds or tens of schemas that change continuously, and you have the production team, especially when the team are kind of split. So you have an application team building logic, and then you have a data infrastructure working on the data side. So disconnect out of the box usually doesn't work, and so going with different solution, thinking out of how to get a solution that works for you. It's the way to go. Like you can think about the Uber schema that we talked through. You can think about relatively things to consistency. You can build different microservices to actually put that data and make sure it's consistent. And you need to think about some of file compaction that you want to implement as well. You can use it, you can build it, or you can use Tableflow if you're a Confluent customer, of course. And I also want to share a couple of resources that I promised. One of them is talks that dive deep into the connector and exactly where the connector misses. I'll give you kind of a TLDR beyond what we said. Essentially, you have to code the schema. It's a problem. You don't want to deal with it. You put a lot of effort into on your Kafka broker to bring all that data through. We don't want to do it. This is why we did have like what you see with the URI, bringing the pointer of the segment and then having a different service taking care of that. Second talk that was bridging the Kafka and Iceberg divide, diving deeper into the microservices that we build if it's something that is of interest to you. So diving into the materializer and the committer, why two-phase commit, what materializer does, what is segments if you don't know that, how two-phase commit works in Kafka open source. And lastly, CI files, small files is a problem in the analytics world. A lot of us kind of take it as granted, and I appreciate that. It wasn't a thing 10 years ago. People heard small files, didn't know what it means, and so on. But there's a deep dive into what are small files, where they're how does it translate in the world of the query engine and metadata and so on, and why is it such a huge bottleneck. So with that, thank you so much for listening, and I hope you learned something new today.